All right, we talked about Graham-Schmidt process, and that's a way to make all your vectors orthogonal, and then you cut it down and make it look like a unit vector by normalizing it. So the QR factorization is really just kind of like a step further where instead of looking at vectors individually, you can look at a matrix, and then you take the columns of those matrix and then perform the Graham-Schmidt process, and then you have a matrix that is orthogonal, which is to say that the columns are orthonormal. And then it turns out that A can be equal to that times um, some other matrix R, which is an upper triangular matrix. So the QR factorization is that if you have an M by N matrix, then you can factor your matrix into Q times R, where Q is another M by N matrix, the same size as A, except the columns are going to be orthonormal. And then you have another matrix R. Um, and that R is going to be equal to, well, R is an upper triangular matrix. So some facts about, I think we said this already, I hope we did, that if you have an orthogonal matrix, a matrix with orthonormal columns, then its inverse is just the transpose. And so when you multiply the transpose with itself for Q, um, then you get the identity. And this is a way for us to find R. So the process for doing a QR factorization is first to find Q by doing the orthonormalization process. And then figure out what R is by doing a multiplication with QT times A. Okay. All right. Yeah. Orthogonal matrix. So I don't know why they don't call it orthonormal matrix, but when they say orthogonal matrix, we assume that not only is it orthogonal, but it also is normal. I guess unit length, orthonormal. All right, let's try to do an example where we have a 4 by 2 matrix, and we're going to try to find a QR factorization of this matrix. And according to the algorithm, the process tells us to find an orthonormal vector set for the column vectors. So we can rewrite that, I suppose, as x1 and x2. At least that's what we called it. Huh, suppose minus 1, 4, minus 1, 4. So that's x1 and x2. And remember the orthogonalization process, or the Graham-Schmidt process, is that we're going to let v1 equal to the first one. So v1 equal to x1. That's not really much of a step there. And then v2 is going to be equal to something. I think it's x2 minus something. So v2 is equal to x2 minus x2 v1 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 I guess these are dot products. We should put a little dot there. And then multiply that whole thing by v1. So this is going to be x2 minus 1, 4, minus 1, 4, minus, and then we have a quotient. We want x2 times v1, so it's really the dot product of x1, x2. So that's negative 8, 6, positive 6. And then a v1 dot v1 is 4. And then multiply this by minus 1, 4, minus 1, 4. So this is 3 halves. Yeah. Oh, yeah. 1, 1, 1, 1. So this is 3 halves. Negative 1 minus 3 halves. Negative 5 halves. Uh, 4 minus 3 halves. 3, 2, 5 halves. Positive 5 halves. And then we get the same numbers. So this is your V2. Now, in this particular problem, we stop here because there's only 2 columns. But if we had a third column, then we would have to use V2. And I don't know if you guys know this trick here, but instead of using the V2 that we found, we can create a V2 star or prime. I think they call it prime in the book, or maybe they could call it star, where you could just deal with a vector going in the same direction, but not necessarily with this weird magnitude um, where everything's divided by 2. In other words, a suggestion could be to scale this into a set of nicer numbers. So I think I could just scale this by 2/5 or something, right? So everything will just become ones. So we don't have to do this for this particular problem because we're basically done. But if I decide that I want to, if I need a third vector, I could just scale it by an appropriate number so that I'm just dealing with whole numbers, which is nicer and easier to deal with. And so if I had to find a V3, I would use the same V1, but I'll use V2 star instead of V2 because V2 star has, ones and minus ones, and V2 without the star has all these other fractions that I don't want to mess with. Okay, so if you need to go farther with this. So I think that's it. And then now we want to make it into a unit vector. So we need to divide by the square root of the magnitude, or the magnitude, which is the square root of it with itself. So it'll be 1/2. So I think I'll call it U1 is V1, or X1 in this case, divided by its magnitude. So if we take the magnitude of this, we should get magnitude 1. And then U2 will be, instead of dealing with V2, I'll use V2 star and find the magnitude of that is also going to be 1/2 or whatever. So it'll be the same thing except negative 1/2, 1/2. Okay. So now those are our 2 vectors, and this is going to give us, this is step 1. Step 2, we create our Q matrix. Q is just going to equal to 1/2, 1/2, 1/2, 1/2, and then negative 1/2, 1/2, negative 1/2, 1/2. So that's my Q matrix. Okay. Um, I mean, you could do other things like factor out a 1/2 if you want, but that's not a big deal. Although we might want to do that when we do our next step. And our next step is to find R by doing the computation of QT times A. And so we have to find QT. And this is a 4 by 2, so QT is a 2 by 4. That's a 1/2. So that's QT. And then now we multiply that by A. So R is going to equal to Q transpose times A, which is this matrix that we just wrote. Times A, 1, 1, 1, 1, negative 1, 4, negative 1, 4. And let's see, we add them all up. This is a 2 by 4 times a 4 by 2, so our result is going to be a 2 by 2 matrix. 1/2, so I add it all together 4 times. That'll be, is that 2? That's 2, right? And then we have 4, 8 minus 2, 6, 6/2. Is that right? 6/2 is 3. Then we multiply this, negative 1, 1, 1. So this is 0. As they promised, this is supposed to be an upper triangular matrix, so we know that the lower left side will be 0. And then the last one, we got a positive 1, positive 1. So we're going to add everything. 4, 8, 9, 10. Right? Hope that's right. I don't know. Sure. 2 to 5. 5. Okay. So that's it. We could check to make sure that we're, should have started off my MATLAB already, but we'll multiply this to check to make sure that if we multiply Q times R that we actually do get A, and we'll do that check in a second. Yeah. Well, it helps us in ways that the LU would have helped us. It allows us to solve for the AX equals B kind of relationship, and you can replace A with this. And then just like the LU decomposition, we can split it up. But the other thing is that we also worked on getting an orthonormal set of vectors. So this is another way to get a set of orthonormal vectors, or to use the orthonormal set of vectors in a matrix Q. Which, yeah, for other things that we might want to use. Um, yeah, kind of. Yeah, a little bit like that. All right, we said our Q was equal to, so I have to write this as an actual Q matrix. So that's a 1/2, negative 1/2, and then next row 1/2, 1/2, next row 1/2, negative 1/2, and then last row 1/2, 1/2. So this is my Q matrix, and my R matrix is 2, 3, 0, 5, and then Q times R is A, which is what we had before. So there you go. Okay, any questions? So that's a QR factorization. It's just another way to factor or decompose the matrix. And now let's move on to our next topic. Least squares. So what this does is that it gives us an introduction to a general problem. And it has something to do with a theorem that we saw earlier, that the best approximation or the best representation for a vector, if you're given a plane or space or a subspace, you can best approximate a vector by its projection. So here's a discussion for it, or the quick discussion. If you have an AX equals B that doesn't have a solution, the next question might be, what's the closest solution you can get? And so what we do is we create a subspace out of the columns of the matrix A, and then we find the projection of that matrix or that vector B onto the subspace of the columns of matrix A. And if we try to remind ourselves of how this might look like for something to try to visualize in 2 or 3 dimensions, we can start off by saying, well, suppose that your column A, remember we used to call this a subspace W, and now we get to relate it to an actual matrix. So suppose W is the subspace spanned by the column A, and so one vector would be A1, and another vector would be A2. These are boldface or vectors, and they make up the matrix A. So let's say A equals A1 and A2, and these are vectors, so these are, imagine them as being columns. And then imagine B as a vector that's not on that space, that's not in that subspace. So if B is not in that subspace, it's not in the span of those two vectors, A1 and A2, then that means we're not going to get a solution to this equation AX equals B. So what's the closest you can get? Well, the closest you can get, if you remember the notation that we used, is that we can project the vector B onto the subspace, and then we'll call this I think we called it B hat. So that B hat is now on the subspace W. So then that would have a solution. Right? Remember those vectors that we've had? We also had a B minus B hat. which is perpendicular to the subspace that we had.
We are that's what it says. Class at a coffee shop. It says class canceled at 4 p.m. today and first Saturday. You don't want them. 90% of the time it's just telling you, hey, there's an earthquake drill. Hey, the earthquake drill's over. Like, thanks. The shouting guy in the blurred alarm doesn't tell you that.
How did you get that? I didn't get that. Yeah. Yeah. All right. All right. So we'll do stuff online if we're not going to meet on Wednesday. We got this our schedule for Monday Wednesdays are kind of weird. All right. Let's come back to this idea for a second. So, all right, ready? Okay. So, what we have here is what they're saying is that B hat is going to be our best approximation for this B vector that we have. Now, where's B hat here? There's no B hat anywhere. So our B hat is represented by this vector. So our x, we're actually solving for x. And we're saying, okay, we don't have a solution for x. That means x is not in the span of the column vectors. And so what we do is we create this vector by projecting B onto the column space. And then we get this B hat. I should call this B hat. And then how is B hat related back to our x and ax? Well, it's going to be a times x. And so the x hat over here is what they're talking about as the best solution. So these other vectors here, ax, they're saying, what if I choose another vector x so that ax is somewhere else on this plane? Ax. I could have a lot of different possibilities depending on what my x is when I multiply it by a. And so I could be anywhere on this plane. And what they're saying is that the smallest number you can get if you were to find a difference between b minus b hat, the smallest number you can get is this projection vector. So we'll see this a little bit later, that b hat is actually ax hat. And we have to find out what x is. Eventually, our solution is going to be in terms of x. And we'll get to that in a second. All right, so that's the least squares problem. Here are a couple of notes. So note, for any vector x, a times x is in the column space of A, because what you're doing there is that whatever value you pick in for x, whatever vector you pick for x, you're going to apply it to a times x, so you're going to be within the column space. We're looking for x that makes ax a point in the column space, or I should probably say a vector in the column space. Yeah, there it goes. I got it now. I didn't think you were. So ax is going to be vector on the column space that's closest to b. If b is actually in the column space, then you actually get a solution for the original ax equals b equation. But if b is not in the column space, according to the best approximation theorem, which we kind of saw and we kind of quickly, like in 2 seconds, illustrated with our plane model over here last time, we saw that there is a vector that best approximates that, and that vector that best approximates that is the projection of B onto the subspace. In this case, the subspace is the column A. And then also B minus B hat. So B is that vector that's not on the plane. B hat is the best approximation that's on the plane. And when you subtract them, you get that vector that's exactly perpendicular to the plane. And so B minus B hat is in the perp, in the orthogonal space. Okay? So let's see if we could do an example. Use the projection formulas to find the least squares. So let's do this example, see if we can get through it quickly. And I'm just going to use MATLAB to expedite things, because it's really just a bunch of computations that we need to worry about. So I'm going to say my A matrix is going to be this matrix here, minus 1, 2, 2, minus 3, minus 1, 3. And then my B vector is going to be 4, 1, 2. Oh, it's a vector, so let's take the transpose of that. So if I were to row reduce this, if I were to make a what's that called, augmented matrix, and row reduce it, let's see if I can do that. RREF is row reduce. We want to row reduce matrix A with B attached to it. What's this say? It's an inconsistent system because remember that last column is supposed to be the B matrix, right? So if we work out the B matrix, we get 0 is equal to 1. And so let's see. Minus 1, 2, 2, minus 3, minus 1, 3, 4, 1, 2. This eventually gets RREF 1, 0, 0, 0, 1, 0, 0, what? 0, 0, 1. So if you imagine, it looks like just an identity, right? But if you look at it as an augmented matrix, then our last row tells us that 0 is equal to 1, which is a contradiction. So this is inconsistent. So what we need to do is we need to project B onto the span of the two vectors in the columns of A. So how do we do that? We had to orthogonalize it first, right? want to do it. So we have x1 and x2. I think we just need to orthogonalize it, and then we need to do the projection. So x1 will remain x1, x2 will be x2, or v2 will be x2, 2 minus 3, 3 minus, what is it? x2 dotted with x1 divided by x1 dotted with x1 times x1. So x2 dotted with x1 is 2, negative 2, negative 6. That's negative 8, negative 3 is negative 11. And then x1 dotted with x1 is 1, 4, that's 6. So what do we have? I don't know. Can't reduce 11, 6. So 2 minus, minus, and a minus. So eventually a minus. 2 minus 11, 6. That's 12, 6 minus 11, 6. That's 1, 6. Is that right? And we have a minus 3, minus, minus, and a plus. So that's a positive. So I have negative 3 I want to add to 22 over 6. So over 6, 3 is going to be 18. 22 minus 18, 3. 3 over 6. Oh, I don't know. Is that right? 2 over 3. And 3 minus, minus, minus. So it's going to be positive 3 minus 11, 6. 18. 7. Are they all positive? All right. So it looks like we have, again, I'll use V2 star here and just take away the 6's. So I'll multiply everything by 6. It'll be 1, and this will be 4, and this will be 7. 1, 4, 7 will be a nicer vector to deal with, because I want to project B onto the span of x1, or V1. So V1 and V2 would be a orthogonal basis. It's not orthonormal because it's not unit length, but at least it's an orthogonal basis for the column, the subspace of column A. So if I want to project B onto column A, that's what B hat is. That's the B that we're looking for. Then I essentially, the projection is the one without a minus sign. So the projection is going to be B dotted with V1 divided by V1 dotted with V1 times V1 plus B dotted with V2, and we'll use V2 star instead of V2 because it'll adjust itself anyway. So we'll use V2 star just to make our computations a little bit easier for ourselves. Okay, so let's find out what this vector is. Um, this would be your b hat, yeah. So this will be your b hat. So this is equal to b times v1, that's -4, plus 2 minus 2. So that's -4 divided by v1. We did v1, v1 already. That's 6. And then b1, v1. So that's -1, or I'm sorry, that's 4. Plus 4 is 8. 8 plus 14 is 22. And then v2 star dot it with itself. So that's 1, 16, and 49. 66. All right. Oh, let's work this out a little bit. 4, 6, -2/3. And this is divide everything by 22, yeah? Third. So positive 2/3 plus 1/3 is 1. -4/3 plus 4/3, that's 0, right? And positive 2/3 plus 7/3, 5, 9/3. No, what's 9/3? 9/3 is 3. So that's B hat. Is that our answer? No. So our answer is supposed to be, so this is B hat. Remember, B hat is just this vector that's on the plane that's closest to B. But we want to relate that, and B hat is actually, we want to solve for X hat is what we're looking for. So yeah, so AX hat, AX hat is equal to B hat, and this is what we're looking for. We want, this is the X that's going to give us closest to that position. So what was A again? A was equal to -1, 2, -1, 2, -3, 3. Why is there an M there? -3, 3. X hat is equal to 1, 0, 3. Now, is this going to be a consistent system or inconsistent, or do we know or not know? This should be a consistent system because B hat is actually on the plane. It's actually in the column space, which is what they said. If B hat's in the column space, then you're going to get a solution for this. So we should be able to get a solution for X hat. Okay. Tired of doing things by hand now. Let's punch it in there. So let's say B hat is equal to 1, 0, 3. And so we do RREF on A and B hat. We get this. 103, 1, 0, 1, 2, and 0, 0, 0. So our -1, 2, 1, 2, -3, 0, -1, 3, 3. if we do our augmented matrix and do the RREF, you get 1, 0, what was it, 3? 0, 1, 2, 0, 0, 0. So it looks like, I don't know if we knew that already, but it looks like our x is going to be two-dimensional. It just says x1 and x2. And over here, I get x2 is equal to 2, and then x1 is equal to 3. So those are my solutions. So those are my x hat vector is 3, 2. And this is the vector when we apply it to A. This is the vector that's going to get us closest to our B vector. Okay. So imagine we're just stuck on this plane. We're trying to reach this vector B that's not on the plane. So the closest we can get is just the shadow of that thing on the plane. Matt? Okay. What? Oh, okay. We could. Yeah. So the fact that we're only dealing with this in R3 and then we start off with a two-dimensional space means that we can visualize this. But in general, you know, these things are going to be hard to visualize. So we have, in R3, we have two vectors that we're dealing with that span the plane. So that's -1, 2, -1. Oh, I want this to be a vector. So that's one vector. And then my other vector is 2, -3, 3. So do you know where I got those two vectors from? They're columns of A. So if I make a plane out of this, and let's see how I'm going to make a plane out of this. The plane is going to be U times this plus V times so this plane contains these two vectors. I'll make it transparent a little bit and make my plane go out a little bit wider. So this is a subspace. It's a plane passing through the origin. It's a two-dimensional subspace in R3. Okay, we know all that stuff. And it's spanned by these two vectors, which means that technically this is the subspace. This is the column of A subspace. Call A subspace. All right. Now where's vector B? Let's get vector B going here. So B was what was B? Anybody read it out to me so I don't have to go there? 4, 1, 2. So vector B is not in the subspace that we want, right? So we have an issue with that. In fact, if we tilt it so we can kind of see, tilt it so we're kind of looking at the plane flatter, we see that vector B is this red vector. Now, we did a projection, and we got a new vector. 1, 0, 3. So now that vector is on the plane. Let's make the plane grow a little bit more. Let's make this a little bit bigger. So that's the projection of this B vector that's not on the plane onto this. And that is the shortest distance that we have from B onto the plane. Okay? So now, unfortunately, this is about as far as we can go. Our relationship between the B vector and the X and X hat vector is coming from somewhere else. But in terms of what we have here, let's see if we can just draw this out a little bit. Maybe that B hat vector was a little too big. So here's what we have. Let's label them. This is one of them. This is A2. This over here is A1. This is B. This is B hat. And B projects onto the plane perpendicular. And then somewhere over here is your X in 2 dimensions. Where the matrix A brings everything over there to this other space. So in 2 dimensions, we have 3, 2, 3, 2. This is the vector that gets sent. This hat goes into B hat via this linear transformation A. So we can think about this as a linear transformation from x1, x2 to the xyz. And then what this is saying is that essentially A x hat is equal to B hat. So when they trying to get B through this transformation, they couldn't get to B via that transformation. So the closest they can get to is to B hat. And the vector that gets you there is 3, 2. 3, 2 will bring you to B hat. It's not ever going to get to B, but you can get as close to B as you can with B hat via this vector 3, 2. Yeah, it's a linear transformation from one vector space to another. And this linear transformation kind of we go into 3-dimensional space, but the image is only 2-dimensional plane in 3D. And so we are not going to be able to get everything in R3, but we can get close to it. Yeah. Yeah. So that B minus B hat, also known as B minus AX hat, because AX hat is B hat, that's going to be the smallest distance we have for any generic X value that you see. Well, no, the B hat is within the span of the column space. So the B hat here, this big vector is actually on the plane. It's a new vector, but it's on that plane that we're looking at. All right. So this process over here where we had to orthogonalize and find a projection and stuff like that could be a little bit cumbersome. So there actually is a quicker way of doing this, which I should have skipped over this and went straight to the quicker way. But at least you get the picture, I hope. And so let's see a couple of theorems that might help us get there quicker. I don't know. Couldn't find a good header. So, what? Yeah, I wrote quiz. Yeah, yeah, it's somewhere back there. So, in the case where B is not in the column space, then we know that we can find a B hat. We're guaranteed that we can find a B hat. And then B minus B hat, remember, is orthogonal. It's that shortest distance, so it gives a perpendicular to the space. It's in call A perp. And so it turns out that if we take the A transpose of this thing, it's supposed to be equal to 0 because it's perpendicular. So if we work through this where B hat is equal to AX hat, and then you distribute the A transpose, then we get this special relationship between B and B hat. In fact, it's a good way for us to figure out what X is. In fact, it's going to be probably in the next line, but I'll take this equation over here. And remember, we're looking for X hat. We're interested in X hat. So if I solve for this, maybe I could just multiply by the inverse of A transpose A. So X hat is going to be, I need to multiply that on the left side, A transpose A inverse of A transpose times B. So instead of going through all that mess of trying to orthogonalize and find the projection and stuff like that, if we could just figure out what this is equal to, then we're probably going to be all good. Yeah. The fact that that B or B minus B hat, I guess that wasn't explained clearly. B minus B hat is perpendicular to A column A. Well, it's perpendicular to call A, so that's to say B minus B hat is an element in call A perp. Um, the thing is that B minus B hat, if A is not a square matrix, B minus B hat applied to A doesn't make sense. And so we have to take the transpose of A for this to make sense. Because, yeah, if A is an M by N, then B should be a 1 by M matrix. It makes a matrix multiplication not only make sense, but I think it has. You also have to apply it to the rows instead of the columns of A when you do the dot product. That comes from the fact that this is a 1 by M matrix or 1 by M vector. Not that it determines that. It should always be A transpose. Yeah, let's just say it's a rule for now until I figure out a better way to explain it.
I'm willing to accept it.
All right, accept it then. Okay, so the key is to find this A transpose A and find the inverse of that. And there's an actual theorem, I think, should be coming up, or definition and then a theorem. So let's just get that stated here. And we'll come back to the same example and we'll see, maybe it'll be easier. Hopefully it'll be easier. So this relationship A transpose times B is equal to A transpose A times X is known as a system of normal equations for AX equals B. And this will play into what we're going to do in the next section, which we'll probably just end up recording and have you guys look over since we're going to miss Wednesday's class. We're going to apply this to an actual application in statistics where we take a look at the least squares line, at the least squares problem. So that's just a definition. You got a normal equation. And so the set of least squares solutions coincides with the non-empty set of solutions for the normal equations. And then they say X, but because if B is not in the column space, the original equation AX equals B will be inconsistent. And so instead of using X, we want to use X hat to say that this is an approximation or the best approximation to your solution. All right. So the bottom line is we have this relationship that we want to use to solve for these least square problems. So we'll use the same problem. And see if we can find a solution quicker. So according to this, we need to find A transpose, multiply with A, and then take the inverse of that. So we need a couple of things. So we need A transpose, choose this color first. A transpose is going to be -1, 2, -1, 2, -3, 2. And we're going to multiply that by A transpose times A is equal to -1, 2, -1, 2, -3, 3, -1, 2, -1, 2, -3, 3. This is a 3. And what are we going to get? Again, is we have wait, I did that backwards, huh? Okay, let me write it correctly. A transpose first. I have a 2 by 3 times a 3 by 2, so last I'm going to get a 2 by 2. So that's a 1, a 2, 2 times 2 is 4, that's 5, 6. So this is going to be 6. And then I get a -2, -6, that's -8, -8, -3, that's -11. Right? Now, as I do the second row and apply it to the matrix, you'll see that the second row dotted with the first column of the matrix is the same thing as the first column dotted with the second row of the matrix. Notice that? And then the second row and the last row, well, I guess that's different. So that's 2, that's 4, plus 9, plus 9. Is that 9? 9 plus 9 is 18, plus 4 is 22. So that's my matrix. We'll do this a few more times, and we'll notice that when we multiply A transpose times A, regardless of what A is equal to, you'll always get a matrix that looks like this. This is called a symmetric matrix. If you draw a line into diagonal, diagonals can be anything. But if you draw a line into diagonal, the opposites will be the same. Now, 2 by 2, it's not very interesting. But if you get a larger matrix, imagine the symmetry between the upper right hand and the lower left hand. That's called a symmetric matrix. We'll dig into that in the next chapter. So we have A transpose times A. We need the inverse of that. A transpose A inverse. Now this is a 2 by 2 matrix, so we know the inverse of a 2 by 2, right? It's 1 over the determinant times the matrix where we switch the diagonals and negative the wings. So what's the determinant? 6 times 22, 132 minus 121, 11? So it's 1 over 11. So that is that. We need A transpose B as well. So A transpose is this, minus 1, 2, minus 1, 2, minus 3, 3, times B, 4, 1, 2. So we got negative 4 plus 2 minus 2. So that's just negative 4. And then we have 8 minus 3 is 5. 5 plus 6 is 11. Is that right? Okay. I hope that's right. Does that look right? So x hat is going to be A transpose A inverse, which is we got calculated already. A transpose B. So that's 1 over 11. I suppose, no, we can't. There's a 6 in there. 22, 11, 11, 6. And then minus 1 or minus 4, 11. So what's this going to equal to? Let's do this first. 1 over 11. So 22 times 4, negative 88, plus 121. 33. And negative 44 plus 66. 22. So that's exactly our solution from last time, where we kind of did everything from scratch from the projection point of view. But now we did it according to the theorem, and we got the same result, which is good. Okay. So I don't know, did you feel that this was a little bit quicker? So this is a little bit quicker with the transpose, invoking the transpose stuff. All right. A couple more theorems, or one more theorem, and an example that we won't have time to do. Oh, this is the theorem that just basically says what we just did. else? So another quick theorem that brings us back to the QR factorization. Another good reason why to have a QR. So if you can rewrite your matrix A and do the QR factorization for the matrix A, then you can find the solution a little bit quicker if you already have the QR factorization, that is. And the solution to your least squares problem is going to be the inverse of R times the transpose of Q times B. And instead of finding the inverse of R, you can just use R, because R is an upper triangular matrix. It's easy enough to do a back solving from this position. Okay, so that is section 6.5. We're gonna do 6.6, but I'll make a video 6.6. I'll take a look at last year's video, but I think I'm gonna prefer to actually make a new video and then have you guys do some a MATLAB kind of problem from there. All right, yeah. I don't know if we can. I think if it was a lot of days, then yeah, but technically this is only one day. All right, so you guys have a good Thanksgiving.